Okay, in a previous video, we talked about substitution, and that video was concerned with indefinite integrals, and that is the integrals that have no limits of integration. So what we're going to do here is we're going to recap what that was. All right, well, we have some integral that looks like this. It says the integral of f of g of x times g prime of x dx. Okay, and let me switch colors on that one right there. There we go. So we make a substitution, and that is to say that u equals g of x, and then we're going to say that du equals g prime of x, and it should actually say g prime of x dx. Okay, so then we're going to highlight that in green. So when you make the connection, you do the substitution, you get f of u, which was your g of x, and du, which was your g prime of x dx. So that's what that substitution looked like. Well, for definite integrals, it's no different, okay? It is the same thing. What happens here is that the limits of integration go from a to b to g of a and g of b. And this actually enables us to work with a much simpler integral. So I'd argue that definite integrals are a lot easier to work with when you can go and substitute. So what I'm getting at is that this a, you plug into g, and you get an output of a new limit of integration. And then the same thing happens with your b. You plug that in there, and you get a new output for your limit of integration. So you get that little combination there. And it's actually not terribly difficult. So what we're going to do here is we are going to do some substitution by picking good values of u, finding du, making the substitutions, changing the limits of integration. We're going to integrate and make this as simple as we can. So let's go ahead and take a look at this first problem here, number 1. So when I look at this one, I say, okay, well, what's u? Well, a good choice of u is something where you have a function, typically if you see it inside parentheses, that's a good hint. But oftentimes you may have multiple set of parentheses. What you are looking for is something where you can take a derivative and find the derivative within the function. So if I say u equals 4 plus t squared, well, let's think about what du might be. Well, du might be 2t dt. That is the derivative. And it's easy to see that du, which is 2t dt, is actually already present. So you're in good shape. So what we see here then is that this right here, 2t dt rather, represents du, and this right here in the denominator represents u. And so what we're going to do is we are going to adjust the limits of integration. And let me go ahead and do that and show you what I mean. If before it was from -1 to 0, you're going to plug in -1 and 0 into your u. So 4 plus, in this case, 0 squared is 4. And then -1 you plug in, 4 plus a -1 squared, well, that means that you get 4 plus a +1, which is 5. So while it may seem backwards or in reverse, it's actually perfectly okay. All right? It is perfectly okay. So what we're going to do here is, now that we've adjusted the limits of integration, this allows us to not have to back substitute whatever u was. Okay, because we simply evaluate the limit with the new limits of integration, and it actually makes it really nice. So let's see here. Adjusting the limits of integration, we now have an integral from 5 to 4, and we see here that we've got du in the top, and in the denominator we have u cubed. And so we can rewrite this so that we can easily integrate. So we're going to go from 5 to 4 again, but in this case it's u to the -3 du. And now we are ready to integrate. What we're going to do, remember, to take the antiderivative, you add 1 and divide by that new power. So we end up with u, -3 plus 1 is -2, divided by -2. Okay, and it looks just like that. And so when we clean this up, okay, and remember we're going to evaluate it from 5 to 4, but when we clean this up, it looks like this. negative 1 over 2u to the second power. All right, again, evaluated from 5 to 4. And so we apply then the fundamental theorem of calculus, and that is that in the antiderivative, we plug in the limits of integration. And so again, no need to back substitute here. We're in good shape. So let's go ahead and plug in our 4, and then we're going to subtract, okay, and a negative 1 over 2, and we plug in our 5. Okay, the two negatives there make for a positive. And what do we get? We get negative 1 over 4 squared is 16. Okay, 16 times 2, 32. Plus 1 over, and then 5 squared is 25 times 2 is 50. And so you do your part to find a common denominator throughout all of this, and I'll leave you to that simple calculation. But find a common denominator and then subtract or add these fractions. All right, and you will end up with something that looks like this, negative 9 out of 800. And so we have a fraction that looks like that. Okay, nothing to it. Again, the beauty of this is that when we adjust the limits of integration, we do not have to go back and back substitute. Okay, so keep that in mind as we work on the next problem. Okay, so here is the next problem. Let's pick our u, all right? And let me switch colors on you here. Our u will be, in this case, 9 plus 5r squared. All right, now you have to start looking and analyzing these functions so you can figure out what to pick for u, all right? But then once we figure out what u is, du is a lot easier. In this case, du is 10r dr. So really nice because we don't have to manipulate this in any way. We've already got our du and we've got our u. All right, and so we rewrite this, but before we do that, we adjust our limits of integration. So 0 to 1, originally, we plug in 0, for example, 9 plus 5 times 0 squared. Well, that's just 0 on the right, so you're left with 9. And then you plug in 1, 9 plus 5 times 1 squared. Well, 9 plus 5 being 14. So our new limits of integration are 9 to 14, and we will write our integral as such from 9 to 14. And we have du in the numerator. In the denominator, we have a square root of u. Okay, we have a square root of u. So we've got to clean that up a little bit just so that we can get it to integrate nicely with the power rule. And so we're going to write this as u to the negative 1/2 power du. And now we are ready to apply that power rule, the antiderivative. Okay, so we're going to say, well, u to the negative 1/2 plus 2 over 2, because we remember you add 1. So that right there is 1/2, so we're going to divide by 1/2. Okay, and again, we're evaluating this from 9 to 14. And so when we clean it up even more, well, the 1 over 2, when you're dividing by 1/2, it's actually the same as multiplying by 2. So we end up with something that looks like this, 2u to the positive 1/2 power, evaluated from 9 to 14. And so we clean this up just a little bit more by plugging in, and we're going to say, okay, well, this is 2 times 14 to the 1/2 power minus 2 times 9 to the 1/2 power, all right, which is a no-brainer there because, I mean, you end up with 2 square root of 14 minus 2. Square root of 9 is 3, so 2 times 3. And we end up with a final answer here of 2 square root of 14 minus 6. And really nothing to it. I mean, that's relatively easy. I think the time-saving part of not having to back substitute makes this really nice. So you could proceed without adjusting the limits of integration, but you are going to have to go back and back substitute. And so that kind of makes things a little bit trickier for you. So again, I advise adjust the limits of integration so that you can save time. But let's go ahead and take a look at another example. And in this case, we're going to look at an example involving trigonometric functions. Okay, on this example, we are looking at some trig functions that are in play here. And so we've got to pick out what u is. Well, in this case, what I see is a cosine squared and a sine. So I think the best thing to do is pick cosine to be your u. So let's think about this for a second. If u is the cosine of x, what is du? Well, the derivative of cosine is negative the sine. Okay, so negative sine x dx. All right, now I've got my sine there. What I'm missing is the negative portion of it. So let's go ahead and just take a look at this one more time. Again, I'm not going to adjust any limits just yet. So I'll stick with pi over 3 to 2 pi. All right, I'm going to rethink the way that this looks by saying, well, it's just a cosine of x squared. Write it out like that. Now I notice that I'm missing my negative sign, so I'm going to make it happen. But by consequence, I also need another negative sign on the outside. Now I believe I'm ready to do my substitution. So let's consider what we've got. I've got my negative and I've got my sign, and what I'm missing here is the dx. But there it is now. Okay, so I've got my negative, I've got my sine x dx. That right there is my du. And this right here represents my u. Now I think we're good so that we can adjust our limits of integration. So we're going to go from pi over 3 to 2 pi. All right, and so we're going to plug those values into cosine. Now you should by now have a working knowledge of the unit circle and these values. So the cosine of pi over 3 you plug in and you end up getting something like this, 1/2. Cosine of 2 pi you plug in and you end up getting 1. Okay, so those are our new limits of integration, and now we are ready to make our substitution. So our adjusted limits of integration are from 1/2 to 1, and we end up with something that looks like this, 3u squared du, which, okay, this is a lot better. I'm sorry, it's negative 3u. There we go. This is a lot better than going back and plugging into pi and all that stuff, or plugging into cosine or sine. So this is really nice because this is a very straightforward integral from here on out. We end up getting negative 3u cubed divided by 3, evaluated from 1/2 to 1, which boils down to negative u cubed because the 3's are gone. Okay. Oops, give me 1 second there. So we get rid of those 3's like that. And then we're ready to evaluate. So what we're going to do is we're going to say, okay, I have negative u cubed evaluated from 1/2 to 1. And I get something that looks like this, a negative of 1 to the 3rd power minus a negative of 1/2 to the 3rd power. Okay, and it looks like that. The minus makes for plus, and so we end up with something that looks like this, negative 1 plus 1/2 cubed is 1/8. Okay, 1/2 cubed is 1/8. We do that subtraction and we get negative 7/8 as our answer. So again, really nice examples on definite integrals and how to apply the substitution rule. As always, I hope this video was helpful, and remember, like and subscribe.